Section 14.4, we're going to look at the second half of this section today. We had done all of the learning work last time. Actually, all of the details, we've covered them all. I'll run through them real quickly. But what we're set to do today is to simply decide on a particular problem which process we're going to do. So we're going to be some problem solving stuff today, basically. So as a reminder of where we had encountered factorials. A factorial means that you multiply that whole number by the whole number down from it all the way down to the number 1. If you have 0 factorial, it is the number 1. We had taken a look at 4 different counting methods. Counting method 1 is the fundamental principle of counting. It comes from chapter 2 originally, and it talks about if you have 2 or more stages of a situation, so they call them events, then you can multiply the number of ways each of those events can occur. And we had seen an example, just as a reminder, of Pizza Planet. And so we had a meal deal where we were choosing the salad, the pizza, and the dessert. Those were the 3 different events, and we multiplied the outcomes of each of them by one another. Our second strategy was permutation of like objects. So if we have R1, R2, ... several things that are somewhat alike within their own category, we add them all together. There's n elements total. Then the number on top is the total number of elements, and the numbers on bottom are each of the things that are indistinguishable. And just as a reminder, we had done an example like with candy. So we had done Starburst. There were 14 total Starburst. And then within each category, red, pink, yellow, and orange, they're indistinguishable, right? So every red Starburst is indistinguishable from every other red Starburst. So we divided by each of those 4, 5, 3, and 2 factorials because it doesn't matter what those are distinguishably different from among. So we divide that out, kind of like removing double counting or repeats. Third strategy was permutation of unlike objects, so things that are truly different from one another in the way that they turn out. So we have n objects, and we're choosing r of them. So we have n factorial on top, just like on the permutation of like objects. And then it's n minus r on bottom, because if r objects are the ones we've chosen, then n minus r are the ones we didn't. And so those n minus r objects are indistinguishable because they were not chosen. So when we did this, and we did an example with contestants earning different prize money in a raffle. So there were 30 contestants, 3 win. The 3 that win different amounts, $100, $50, or $25. So the order matters. I didn't mention that, but it's boxed in over here. Order matters for permutations. And then the denominator is 27 factorial because those are the people who didn't win anything. So, loser number 1 is indistinguishable from loser number 2, basically. So that's why we're dividing by those. And then our fourth strategy is a combination. A combination is very similar to a permutation in the sense that all the objects are uniquely different, but the order doesn't matter. And so the notation is NCR, C for combination. N factorial is still the number on top that we have to choose from. And then in the bottom, not only do we divide by the number who aren't chosen, n minus r, we also divide by the r factorial as well. Because in this situation, it doesn't matter if you are first, second, or third, as our example with our contestants, you win the same thing every time. So you are indistinguishable whether you're chosen first or third. If you're a winner, you're a winner. So all the winners are indistinguishable, that's the 3 factorial, and all the losers are indistinguishable, that's the 27 factorial. Okay? And we are here. So we're here taking a look at examples. And I mentioned this last time, but I will mention it again. Sometimes there's more than one way to do a problem. So I'll mention those as we see them so that you can kind of have that in your notes as well. Even as I'm writing the exam, and the exam is written, there's one of them in there where, at least one of them, because I can remember off the top of my head, where I have 2 answer key choices because there's 2 distinguishably different ways to do the problem. There's just 2 different ways. So don't always necessarily think that your work has to match up with somebody else's. If you're getting the same answer, it may be that there's more than one way to do the problem. That's a possibility. Okay, so here's an example. We have phone numbers in a large business. They start out with 405767, okay? So there's 4 more numbers at the end, and it wants to know how many different phone numbers are possible. So we have 4 strategies. We have fundamental principle of counting. We have permutation of like objects, permutation of unlike objects, and combinations. So Which one do you think this might be, or ones if you think there's more than one? Any thoughts? Okay, let me ask a couple questions then. Does the order of the last four numbers matter? Yes. It should. If you mess up somebody's phone number, you're not going to get a hold of them, right? So the order matters. So that eliminates something immediately. What does that eliminate? It eliminates a combination. Okay, does that make sense? So if you can't figure out which one to go with, at least start figuring out which ones to eliminate. It's not a combination. Are those objects at the end alike? So what I mean is, are they distinguishably different? Can you tell it apart if you mix them up? And the answer is, yeah, you can, right? It matters if you put the 4 or the 3. All of those objects are different objects. Every object's different from every other one. Bailey?
But what if you have like all 3s?
That's okay. That doesn't mean that those are indistinguishable. I'm saying within each of the number slots themselves.
Oh.
Yeah. So this one's not a permutation of like objects because none of our objects are alike. A 3 is different than a 4, right? They're different values, so it's not permutation of like objects. So we're down to looking at whether it's a fundamental principle of counting or whether it's a permutation of unlike objects. And let me tell you the difference on this one so that you can see why it's going to be which one it is. How many numbers can you put in this spot right here? How many choices are there?
10.
There are 10. How many choices are there right here? There's 10. And let me pause for a moment because I want you to recognize if this could be done with a permutation, the numbers would have to be decreasing. Think about how we wrote that formula out, right? It was decreasing. We had 30 times 29 times 28. That's not happening here. So why is it not happening here? Well, because in the situation with a phone number, the numbers can repeat, and that's okay, right? I could have them be all 3s like Bailey said, right? Like that's an acceptable option as the last 4 digits. So this one is a fundamental principle of counting, okay? And the way that we do that is we recognize that there are 4 different choices that are being made, or 4 different events, an event of choosing each of those 4 numbers. And as we've already started writing out above, there are 10 choices for each one of them. And the fundamental principle of counting says that I would then multiply these numbers together. What number does that give me?
$10,000.
10,000. One quick way to catch that is that how many zeros are in the number 10,000? 4. How many 10s did I multiply by? 4, because there's 4 zeros, right? So it shows up again. So there are 10,000 numbers that could work here, right? So I could legitimately have 10,000 different phone numbers in this system and not repeat anything, right? They would all be different. Okay, so we could have 10,000 people's extensions, if you will, on this situation. Let's try another one. All right, a worship team practices 8 songs on Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? All right, so what do we think? So you think it's a permutation of like objects? You think it's a combination? Okay. So let's run through them, and we'll just go from start to finish on which ones can or can't work. There's actually 2 that work on this one, okay? So the first one we have is fundamental principle of counting. So if you are in a service and you're creating an order of worship, okay, and this would be true if you were doing a concert. It doesn't have to be about a worship service, but it would be true for a concert and things like that as well. And you have 5 songs that you're going to sing. Then there's 5 different slots that you're going to choose. Does that make sense? So the fundamental principle of counting will work on this. That's one object or one option because I'm making 5 choices, one after the other. Now, unlike the last one, I'm not going to have the same number in each spot. Does that make sense? If I'm going to change my song, I need to choose a different song. So the first song that I choose, I would have how many choices? There'd be 8. But once I've chosen that song, I don't re-choose it if I'm trying to, fill out the rest of the worship set. So how many would I have in my second song? 7, and then, and 4. Okay, now it's important for me to pause for a moment to recognize that this one works, and it works like this. This is correct. But I need to address the possibility of the combination that was mentioned before. Because if you do a combination, it sometimes feels like it could be done like this as well. Okay? So why is it not a combination would be the question. So what is the key feature in a combination that sets it apart from a permutation? The order doesn't matter. Okay? So does the order matter in this process, in this particular problem? It does for a couple of reasons. One might be the language that's being used. Can you see the language that tells you here that the order matters? It's right here. It says, in how many ways could the songs occur? Occur means happen, right? They take place. If I changed this language to say, in how many different ways could I choose the songs, right? Just have a collection of songs, then the order wouldn't matter. It's just the songs I'm going to choose. This one specifically says I want the order to be a consideration because it says they're occurring in a specific order. Another thing about this in general that makes it feel like it should matter is that if you think about a worship service or a choir concert or something like that, the order in which things are sung typically matters anyway. There's usually some sort of a rhythm or a feel to the way they develop, right? Worship service specifically, right? You don't have a fast song and then a slow song and then, there's a structure that makes it different, the order mattering, okay? But the language itself really does tell us that this is the order that we're looking for. The order matters. So it's not a combination. It could be done with a permutation. I know we have to multiply these still together. We'll get back to that in a second. But it could be a permutation as well. So within a permutation, the order matters. There are 8 songs. So this is a permutation of unlike objects because the songs are distinguishably different from one another. There are 8 songs that I'm choosing from, and there are 5 that I'm choosing. I didn't mean to put a C there. I'm sorry, I meant to put E there. Fix that if you have that written down, I'm sorry. 8 songs I'm choosing from, 5 that I'm choosing. So I have 8 factorial on top because that's the number I'm choosing from. And then on bottom, it's the number I don't choose. So 8 minus 5 or 3 factorial. There are 3 songs that are not chosen. And notice if I write this out, 8, 7, 6, 5, 4, and 3 factorial, do you see what happens with my 3 factorials? They're going to cancel, and what happens on the top? It's the same list of numbers that we had when we thought about it as a fundamental principle of counting, okay? So either way, we're going to multiply the same values together. So somebody go ahead and grab a calculator, multiply those out for us. 6,720 ways that the songs could occur, right? The word being occur. Okay, how are we feeling so far? Okay. Our next example has 3 parts to it, okay? It's cards. So I want to run through some features of a deck of cards because not everybody's always familiar with the cards the same way everybody else is. So if you're not as familiar with a deck of cards, you might want to write down a few of these details so that if you see them on your homework or if you come back to them in a test, you'll have that in your mind. So in a deck of 52 cards, there are half of them red and half of them black. So there's 26 red, 26 black. Okay. There are 4 suits: hearts and diamonds, clubs and spades. 2 of the suits are red, that's the hearts and diamonds, so there's 13 of each of those. And then 2 of the suits are black, that's the clubs and the spades, so there's 13 of each of those. Okay, within each suit, so let's just say diamonds, there are 13 cards, but all the cards look different. They have a different value to them. So the values themselves range from 2 to 10. Those are our number cards. So there's no 1, and there is the double digit 10. Okay, so 2 to 10. So there's actually 9 value cards, right? Because it goes from 2 up to 10. There's 3 face cards, Jack, Queen, and King. And then there's one that's neither a face card nor a number card, and it's the ace. And depending on the game, ace can be played as the high card or a low card. So it can kind of look like it's above a king or below a 2. And sometimes it can actually change values within the game depending on the game you're playing. Now, in terms of the values being, better or worse than the others, that's nothing of our concern for this argument. But they're all different. So each card's unique. So even though there's an ace of clubs and an ace of spades, they're different because they're both aces, but they're an ace of a different suit. Okay, so the 52 cards are all distinguishably different cards. Okay, everybody good so far? Okay, now I want you to think of whatever favorite game you have that you've ever played with cards, or maybe not a favorite, but a game you've played with cards. So it doesn't matter whether it's, poker or if it's Go Fish. Okay, anyone you have. Phase 10, that's when we play a lot. We play Gin Rummy. We play a lot of different card games when we go to my in-laws for the lake, which I still need to show you a picture of the fire. We will do that in the end. And so lots of card games. So think about what happens in a card game. Somebody deals the cards, and what's the first thing you typically do in a card game once you get your cards? You look at them, and then what? You organize them some way, right? So you've got this hand of cards, and the first thing you do is you move them around. True? So does the order in which the cards were dealt to you matter? Nope, because the first thing you did is to reorganize them into whatever order makes sense for the game, right? Maybe you're putting them in a number order, you're putting them in a suits order, something. Whatever you're doing, you're organizing them some other way. So the order in which they were dealt to you does not matter. Which option gives us that, where it doesn't matter? Combinations. So anytime you're dealing with a card game, you're dealing with a combination, which is kind of nice because they both start with C's. Yeah? Another thing that happens that's very nice is that anytime you're dealing with a committee, it's a combination. So within a committee, it means that let's say you're electing 5 people, right, from a bunch of people, and they're creating a committee. Well, it doesn't matter if you were elected 1st or 5th, you're on the committee. Agreed? Okay, so with a committee is another prime example of where order doesn't matter, combination. Once you start putting people in positions, it matters. So think about what happens when you do most of your elections, right? Think about student government or something like that. You don't elect just a bunch of people. You elect them to specific positions, right? So you've got the position of president, the position of vice president, and whatever's going on. Notice that one too. It's position, and it's a permutation. Isn't this lovely alliteration? They don't always work like that, but those particular ones do, so that's nice to remember. All right, so let's take a look at our 52 card deck. So it wants to know, first of all, just how many different hands can be dealt. So we're doing a combination, is what we said. We have 52 cards, right? And we are going to deal out 5 of them. Okay, does that make sense? 52 charge cards to pick from, 5 of them become your hand of cards. So I'm writing this down as 52 factorial on top. The denominator for a combination is both the cards that are chosen and the cards that are not. Okay? So how many cards are not chosen for your hand? How many cards are not in your hand? 47. So there are 47 cards that are not in your hand. You could feel free to write this in the other order. And there's 5 cards that are. So again, why is the 47 factorial in denominator? Because the order in which those 47 cards are not given to you doesn't matter. Nor does the order in which the 5 cards are given to you matter. This is a really good example of one where your calculator would not be able to do this for you. I didn't mean to do that. Let me redo that. There we go. Your calculator, if you put these in, is not going to be able to do it. You cannot put 52 times 51 all the way down to 1 in your calculator is too big. It's way too big, actually. So it is absolutely necessary that we simplify something before we put it in on this one. Sometimes we have a choice, and this one we do not. So I'm going to write this down to 47. I'm going to stop. And there's that 47 factorial in the bottom. Then I have 5, 4, 3, 2, and 1. And the 47s cancel. Now we looked at this a little bit last time, but the numbers were quite a bit smaller. In some cases, we can sort of pair them or group them up and they just cancel cleanly from on top. Sometimes it doesn't work that nicely, but they all will reduce. For example, if I just go down the list of the numbers on bottom, the number 5 will divide the number 50 and give me a 10, right? Okay. What about the number 4? What could you reduce that with? 48 would be great, which gives you a 12, right? How about the 3? You've got choices, by the way. Okay, maybe more than one option. Yeah, you could do it with the 51 and it would be 17. You could also have done it with the 12 and that would have been fine too. How about the 2? Okay, 52 and 12 or 2 would divide and would give you a 26. Now, if you choose different ones to simplify it with, that's fine. You'll still get the same value at the end. You want to be sure that you're paying attention and carefully circling or remembering all the pieces that are still on the top. So we're going to multiply with the ones I've got here, 26, 17, 10, 49, and 12. And how many cards, hands of cards do you get? Yep, that's right. 2,598,960 hands of cards. It's a lot, right? So this is how you can play the same game over and over and over again, and the results are always going to be unique, right? Okay, it would be very, very strange to get the exact same 5 cards twice. True? Yeah, very strange. In fact, it'd be very strange to get the same 5, like the perfect 5 cards. I have a very specific memory of being a child, and we played Rook. My family did. I haven't played Rook since, forever. But I remember leaving the area, the cards were dealt, and I came back, and I had a hand that had all yellows. Like, that's not really going to ever happen, right? Because my dad was being funny, and he was like going to see what I did if I got exactly the perfect hand. It was a perfect hand. If I got all yellows in that particular game, that's fantastic, okay? So if you're familiar with spades, it would be like getting all spades if you were playing spades. Same thing. It's not going to happen. So it's very uncommon because there's 2,598,960 different hands you could get. So let's see what would happen if we just had all diamonds in our hand, okay? So if we have all diamonds in our hand, that means that we had to have diamonds only selected from. So how many diamonds were there, did I say? There's 13. So there's 13 diamonds. Still, it's a combination, okay? And how many cards are in my hand? 5. Now you might think, well, I've divided the deck into fourths, right? I mean, like this is a fourth of the deck. It'd be about a fourth of the number of hands of cards. So let's see what happens. So I have 13 on top. 5 cards are selected for my hand, and then 13 minus 5 is 8 cards are selected that are not in my hand. So I have 13, 12, 11, 10, 9, and 8 factorial. There's 8 factorial, and then 5, 4, 3, 2, and 1. So 8 factorials cancel. This one's actually really nice to pair some numbers up. Do you see a couple of numbers that you could pair up and cancel something completely from bottom to top? What do you see, Tessa?
5 and 2.
5 and 2 are a fantastic pair. So those two combine and I can cancel the 10. How about the 4 and the 3? That one as well, right? 4 and 3 is 12, so that one cancels that one completely. And if you don't do it in this order or whatever, that's fine. You'll still get all the same pieces. Well, not necessarily the same pieces. You'll still get the same product at the end. So then we're going to multiply 13 times 11 times 9. What do you get? 1,287. That is much fewer than 1/4 of my 2 million, right? It's a lot. I mean, like 1,000 hands is many, but it's not near as many as 2 million. Agreed? So this is an uncommon thing to happen. In fact, if you're playing like poker, this is called a flush. Okay? When you have all the same cards of the same suit, it's called a flush. And it has value because it's uncommon. Okay? Let's do one more. This one is a little different. This one asks us what the probability is of getting that 5-card hand being all diamonds. Okay? Now, we've seen formulas for probability before, but let me remind you what this is. The probability is the number of ways that we can get what we want to happen, whatever that is, divided by the number of ways that anything can happen. Okay, does that sound familiar? That is not a real formula. That is a thinking kind of how we process it kind of perspective. So in this scenario, what we want is we want to get all diamonds. In fact, let me write it this way. This is the number of all diamonds, or you could say 5 diamonds if you wish. That's what we want. And on bottom, it's the number of anything happening, right? So I'm using that N to just represent number of. And these are the values that we got on the previous 2 parts of the problem. Well, there's 1,287 that are diamonds. And then there's 2,598,960 of anythings. Now, we can reduce this in fraction form if you wish. Some of the examples you're going to have will reduce very nicely. You can turn it into decimals and do an approximation if you wish. If you turn these into decimals, I'm going to request that you do 4 decimal places. Okay. This one does work best to turn it into decimals because it is very small. So if we will divide these, what's the decimal form with 4 decimal places for this particular problem? It's an approximation.
0.0004 or 5.
Okay. Did I write that right with what you said, Chelsea? Okay. Yeah, it is 0 point, and you can leave that first part off if you want, but 3 zeros and then a 5, right? That's 5 10,000ths. That's where it is. That's the place value we're in. It is very uncommon. If you multiply this by 100, you can find the percentage. If you multiply it by 100, the percentage is 0.05%. Yeah, it's very uncommon, right? And that's what makes this a valuable or a high yield hand, right? It's a valuable hand because it's uncommon. Okay, let's try another one that does something similar, but with a little bit different context. All right, so we're going to look at a committee. Now, what did I say? Committees are combinations, so we know we're using combinations. It's a committee of 3 people, and we're selecting randomly from 7 seniors, 5 juniors, and 3 sophomores. Okay, so those details are important right here. And we want the probability that it consists of all seniors. Okay, this is very similar to this problem. It's asking about probability. True? So it wants the probability of all seniors. And the way I find probability is I find the number of ways that I can get all seniors. And it's always compared to the number of ways I can get anything. That's how probability is calculated. The number of ways I get what I want compared to the number of ways I get any possible thing. So I need to find 2 things. So this is thing 1 and this is thing 2. Not like Dr. Seuss, but nonetheless. We need to find the number of ways that we can get all, which in this case is 3. I'll write it specifically as 3 seniors. Okay, so how many seniors are there? 7. And we already said it's a combination. And how many am I going to choose? 3. So 7C3. So I have 7 factorial on top. I have the 3 I choose on bottom, and that means there's 4 of the others, right? We had, hang on, are there 7? Yeah, 4 of the other seniors, right, there you go. 4 of the other seniors that are not chosen. There we go. So I have 7, 6, 5, and 4 factorial to cancel with a 4 factorial. And then 3, 2, and 1. So 4 factorials cancel. What do you notice about 3 and 6? They'll reduce, right? But even nicer if you happen to notice that there's 3 times a 2 here that will reduce the 6 completely. Okay, so either way would be fine. So nonetheless, I end up getting a 7 and a 5 when I'm done. So how many different all senior committees could there be? 35. There's 35 of those. So in terms of my formula or my description on top, that's the 35, that's my numerator. And then the second component is finding out the numbers of ways of getting any committee. So the number of anything happening. Well, how many people are there to pick from to create the committee? Total. There's 15. So you should be looking at the 7 here, the 5 here, and the 3 here. 7, 5, and 3. That's 15. And I'm creating a committee of 3 people still, but now I can choose from among any of them. So I have 15 factorial on top. I have the 3 that I choose on bottom, and then that means there's also 12 that are not chosen. Does everybody understand how I'm getting my denominator pieces? Is that making sense? Okay, so I have my 15, 14, 13, and 12 factorial on bottom, or on top, excuse me. Then I have the 12 factorial on bottom, and I have 3, 2, 1. So the 12 factorials cancel. I can't pair these up very well on this particular one, like they don't pair at all. But I can divide the 3 into the 15 to give me 5, right? And I can divide the 2 into the 14 to give me 7. So I have that 5 and that 7, and I have a 13 here. So what happens when you multiply these together?
455.
Yep, 455. So I have 455 on top. I'm sorry, I have 455 that I'm going to put into the first piece, which is the denominator, not on top. But I will go ahead and give you the values here. If you reduce these as a fraction, it's 1 over 13. If you put it in decimal form as an approximation, right, it's approximately, it's 0.0769. That's what it'll work out to be. And I'm good with either answer. There's benefits to each one. In some sense, that decimal expansion, if you just multiply that by 100, you'll get the percentage. It's about 7.7%, right? Not real likely, but way more likely than the hand of all diamonds that showed up a minute ago. Okay, similar question, slightly different question details, but very similar. We want now to have a probability that we have no seniors. So what does no seniors mean? Not necessarily, because you could have some seniors and not all seniors. So you can't just subtract in it, unfortunately. But just think about the words themselves. What would the committee look like if it has no seniors? They'd all be sophomores and juniors. Does that make sense to everybody? Okay, so no seniors means I have all sophomores and or juniors, because it could be either, right? Well, so how many of them do I have that this could be from? Like how many fit that criteria? Like how many sophomores and juniors are there? There's 8, right? There's 8 of these. It says them right up here. There are 5 juniors, 3 sophomores. There's 8 of these folks that are going to comprise that committee if we have this structure. So it sets up much like before. We want the probability of having no seniors. Or you could equivalently say this is a probability of having sophomores and juniors, right? And or juniors. So what we want on top is we want the number of ways of having the sophomores, juniors compared to the number of anything. But I contend we already know one of those numbers. Which one do we know? The anything. It's still the same 455, excuse me, that we had before, right? So that one we don't have to find anything new for, but we do still need to know the number of ways that we get sophomores or juniors. And we mentioned that there's 8 of them that we're choosing from, and how many are on my committee? 3, still 3. So I have my 8 on top, I have the 3 that I'm choosing on bottom, and the 5 that are not chosen. So I have 8, 7, 6, 5, 4, nope, sorry, 5, 8, 7, 6, 5 factorial with my 5 factorial, and then 3, 2, 1. This one reduces nicely as well, so the 5's cancel. 3 and 2 is 6. So I just have 8 times 7, which is 56. So that's my numerator. I'll show you the fractional version, then I'll show you the decimal version as well for approximation. Fractionally, this is 8 out of 65. Okay, that's fine, it's an option. If you want the decimal version, it's approximately 0.1231. So it's slightly more likely, but that should make sense because there's 8 of them instead of 7 of them that I'm picking from, right? That there's slightly more options of the way that could work out. So about 12% of the time, I would have committees that would have no seniors on them, and about 7.7% of the time, I'd have committees that have all seniors on them. And anything else is in between there, right? All the rest of them have some seniors, but not all.